Okay. So Henriette, are you ready?
Yes, I'm ready to go.
Okay, great. So it's great to have Henriette to give the third lecture in the series. Take it away.
All right. So this lecture has to do with divergent soft limits. We talked about the vanishing soft limits and how we could bootstrap effective field trees using those limits. But in this case, we're going to talk about this part that was basically be negative sigma in this weight characterization we gave in the first lecture. So I want to show you some very fundamental cool stuff that comes out from studying these divergent soft limits. So let's go back to your quantum field theory class, where you may have learned about photon IR divergences in the context of QED. So suppose you have some photon, like this one here, and you have a particular diagram. There are, of course, many diagrams that contributes to an n-particle process. But let this photon interact with something that could be an electron or a positron or some charged particle. And then you can see that the contribution from this diagram is something that has a factor of this form here. Qk is the charge that is associated with this electron or positron that sits there. So in some units, it's plus minus 1. And then there's a polarization for the particle that we're going to take soft, the photon. And it's started into the momentum of the electron, and it divided by ps.k, which is basically coming from the momentum of the propagator. So this is basically the propagator term that sits here. So that is ps plus k squared in the limit where, of course, the external states are on shell. So s squared and k squared are both 0. Now you see that as you take ps to 0, the momentum of the photon, this factor that sits in front of the diagram will be dominating what you get from this diagram, and that gives you the divergence. So the logic here is that when I take the momentum of the photon to 0, the propagator will go on shell because this is just a free particle vertex. So it becomes basically k, and k squared is 0, so that propagator goes on shell, and that's where the divergence comes from. And you see it directly because here in the denominator is a factor of ps, and so of course as that goes to 0, this blows up. So then in quantum field theory classes, you talk about photon IR divergences, and you talk about how, well, they sit there in individual diagrams, they sit there in the scattering amplitudes, but once you compute the cross section and take the loops and their IR divergences into account, everything nicely cancels and can give you finite cross sections. So in this lecture, I won't worry about the cross sections or think about those. We'll just think about the amplitudes themselves. And a similar case, a similar thing is true about soft limits for gluons, not just for photons, but also for gluons, as we can see by looking at the Park-Taylor amplitudes that I gave you for gluons last time. So here I chose lines 1 and 2 to be the negative helicity states. And the amplitude is then the cyclic product of angle brackets in the denominator and an angle 1, 2 to the 4th in the numerator. Now I want to take the momentum of particle S that I chose to have positive helicity. I want to take it soft. So I scale my momentum by a factor of epsilon. But now we know spinor helicity formalism, and I know that my momentum is an S angle times S squared. And so I should think about how I'm actually going to do this soft limit in terms of spinor helicity variables, because after all, that's what my Park-Taylor amplitude is expressed in terms of. So should I scale in option 1, the square brackets, or should I scale in option 2, the angle brackets, or should I do some hybrid where, for example, I scale with square root epsilon for both of them? What this comes down to is a little group ambiguity, because we know little group scaling is something that scales the angle and the squares of a particle oppositely. And so these different choices are just equivalent by a little group scaling. But it turns out that there's one choice that is more convenient than the other ones. And that's choice number 2. So this is what we'll do. And the reason is this. If I go with choice 1 and I scale my square brackets, then you see that Park-Taylor only depend on angle brackets. So the result of that would be an order 1 in epsilon. It will not detect the divergence that we know should be there, because just like for photons, there'll be factors that come from this from diagrams that has this kind of cubic interaction. So it doesn't properly detect the divergence if you use option 1. And in option 3, well, there's more to keep track of if I don't both want to scale the angles and the squares. And we go for a minimal principle here. And by the way, who wants to deal with square root epsilons anyway? So we will go with option 2, namely that we'll scale for a positive helicity particles. To take the soft limit, we scale the angles. And again, this is just a technical choice. There's nothing fundamental in it, except this is very practical. Okay, so I scale my angles and I don't scale my squares. That gives me a limit where PS goes to 0 when epsilon goes to 0. And then I go and I look at my Park-Taylor amplitude and I see that there are 2 places in the numerator that contained S. So these are just the last factors in the cyclic trace here, or the cyclic product. And so I pull that out from the rest, and then I multiply and divide by a factor of angle in 1. Why do I do that? I do that because then the entire remaining part over here is exactly an n particle amplitude. So what it shows is that I get a factor that is 1 over epsilon squared, 1 epsilon for each of the 2 S angle brackets. I get something that captures the soft factor, and then this multiplies an n particle amplitude. So it's basically as if you remove the soft particle from the amplitude, and you're left with an amplitude with 1 less leg times a soft factor that encodes the fact that something happened. So by the way, a little exercise for you guys to do if you want to get your hands dirty, which you really should, is to connect this soft factor that I wrote here to the expression that I gave you from photons, which is also valid for gluons, and try to make the connection between this and that expression. It requires a little calculation and some of the techniques you saw last time. Okay, questions, comments? Please interrupt at any time. And I see that there's a question in the chat. If I'm making distinctions between collinear and soft divergences, I'm not thinking about collinear divergences at all. I'm not taking S to be parallel with K, for example, or specific K. I'm just scaling the soft, the particle I want to take soft. I'm just scaling its momentum to 0. So I'm not doing a collinear.
I'm just kind of hallucinating about all the QCD lectures I've seen, and I'm thinking about, you know, summing these guys up, and I'm trying to put you in context.
Right.
I'm perfectly happy looking at this because you know, the words effective, you know, equivalent photon approximation are screaming at me right now, which of course is written down right here.
Right. So maybe see at the end where we are going with this, because you'll see how these are definitely soft limits, and I'll keep them separate from the collinear story, but of course there are connections. So
can I hold the words Weizsäcker-Williams in my head also?
Sorry, say that again.
Can I keep the words Weiss and Williams in my head also? You
can keep anything you like in my head, in your head, but
okay,
you
good.
have to maybe explain it to me afterwards, please.
Okay, good.
Good. All right.
Okay. Yeah.
So more generally, I have written out here some soft theorems, and this may be something that Thomas also recognized, for sure, that these are the soft theorems, and that sort of underlies a lot of the modern applications of soft theorems that has occurred. So let me try to explain what we got here. So here, again, I'm taking a particle to be soft. I take its momentum soft. And we talked about photons already. And there are soft theorems that say that amplitudes with photons behave in a universal way when a photon is taken soft. In particular, it has that 1 over epsilon squared divergence that I just showed you for gluons that sits in the photon 2. And that soft photon factor, that S0 that I denoted here, in spinor helicity language, takes this form here. Now, where did that come from? Well, I told you already that there was a factor like this that came from basically Feynman rules and the denominator from the propagator. If I convert exact expression here for a positive helicity for the photon into the spinor helicity formalism that I introduced last time, then you have this part here that comes from the polarization. Then there's the K. This was this K that was dotted in. Then there's the PS.K. Let's give that a different color. This part here, that sits there in spinor helicity language. And Then there's the x that appears in this expression. This x here that appears is simply this equivalent of the q I gave you last time, which encoded the gauge choice of the polarization vector. So x is arbitrary as long as it's not s. And then when you simplify this out, you see that the sk squares will actually cancel. And you're left with exactly this expression, which is what sits here. And then you have to sum over the k. So that's what that overall soft factor is. And that multiplies the endpoint amplitude, similar to what you saw with the Park-Taylor amplitude. But what is very interesting is also that there's a subleading soft theorem, a 1/epsilon type term. And that also takes a form that I haven't written down here, which is in a sense universal, in that it's basically something that has to do with the angular momentum operator. And so it's a derivative operator that acts on the amplitude. And then in effective field theory context, there can also be another subleading term, which I won't go into too much detail about, but it sits there. Similarly, for gravitons, there's a leading soft factor, which has a similar expression to that for the photon, except now instead of the charge being there, that's the overall gravitational coupling, there's something that basically looks like a momentum of sk. So that you can think of as gravity couples to energy, right? This is the Mandelstam variable that basically sits here. This is actually an sk, so to speak. And then there's something that looks like this polarization stuff over here squared. And we've seen a little bit of a hint already that Yang-Mills is something, Yang-Mills squared, or is somehow related to gravity squared. So maybe it's not surprising that this kind of looks like energy coupled to the photon soft theorem squared. Very heuristic, but it sort of has that spirit. So that's the leading soft graviton theorem. And that comes from, in our way of taking the soft limit, where I scale the angles and not the squares, this comes as in 1/epsilon cubed. This was found by Weinberg already in '65 in a famous paper. Why did he do it? Well, as he says in his paper, he says explicitly, I do it because I can. And he had some other reasons too. But he does say that statement. Then there are subleading soft theorems too, that were found much more recently in 2014 by Cachaso and Strominger. And they also take a certain universal form. And all of this then acts on the endpoint amplitude of the graviton. And in effective field theory context, there are certain cases that can also give you contributions at 1/epsilon. Now, some of you might have heard about things like celestial amplitudes and connections between the soft theorems and the BMS group at null infinity and so on. All of that story arises from these subleading soft graviton theorem and the whole structure of soft graviton theorems as you can derive from these stories. And this is something you can look up in the papers by Strominger and Cachaso. I put a reference to lecture notes by Strominger into the reference file, so you can see it there.
How do you distinguish between A and tilde and AN, and like how do you distinguish between them? They look the same. Like,
sorry, one more time.
How do you distinguish between AN and AN tilde?
So AN has the same external states as AN plus 1 when the soft line is removed. But A tilde and M tilde, those mean that the K state that you can have, that the line that connects to the soft part can be different. So these guys can actually have different external states than the other ones. That's the distinction between them.
Okay.
And so these subleading soft theorems, both for photons and gravitons that modify these are related to effective field theory operators. And these were actually found just about 5 years ago with my student Callum Jones and our collaborator Stephen Schulich. And there are actually also papers by Sen and Latka and others that put these kind of soft theorems into context of string theory and D dimensions and so on. So nice set of papers. Okay, so there are also in the reference that I give you, there are expressions for these subleading factors, but we won't need them for today. So the goal of the lectures today is to derive a master formula from which all the results above can be derived, all these soft theorems, as well as soft theorems for other particles. In particular, any kind of divergent soft theorem in any context of effective field theory in 4 dimension can be derived from that master formula. So it's a 4D master formula. But then the reason I want to show you this is also is twofold. One is that it illustrates a very powerful tool that is very often used in amplitudes, both for deriving recursion relations and for many other things. And that is the idea that we, of course, typically for scattering processes, we would want real momenta, but it's actually very powerful to continue the momentum for for the derivation purposes into the complex plane. So you basically deform the momenta in certain ways. And that's an extremely powerful tool combined with complex analysis. And so I want to illustrate that, and that's part of what goes into the derivation of this formula. And then the second point is that this master formula, not only does it give rise to all the divergent soft theorems that we can possibly have in any field theory or effective field theory context, it also gives you some very fundamental constraints on scattering and properties of quantum field theories that you probably heard about, but you may never have seen a proof of. So let me give you some examples of what these are. So one is that we can derive the equivalence principle from a GR in GR in an amplitude context. So what does this mean? It's basically an amplitudes version of saying that different objects all fall equally in the same gravitational field. Another statement that you have probably heard at some point is that you're not allowed to have higher spin massless particles interacting with gravitons or things with lower spin in flat space. And that statement is sometimes made like, okay, we should just consider up to spin 2, the gravitons. Don't think about spin 5/2, don't think about spin 3. That doesn't exist in flat space. In curved space, it's a different matter, but in flat space, you can't have it. And we can prove from this master formula that particular statement. Well, that's a very nice outcome. So this is something I want to show you. And then another statement you might have heard about is that when you have gravitinos and you try to make them interact, there's one thing that you always must have, and that is that gravitinos must couple to gravity. And the only way they're allowed to couple is in the way that preserves supersymmetry. So you could play around with Lagrangians and write down Rarity Swinger fields and see that they always must couple to gravity and this stuff, but it leaves the question open, like, but would have been something else I could have done at the Lagrangian level? What if? And here we can actually see that this must happen. So I may not be able to show this to you today, but that is an outcome also of this master formula. Okay, questions?
Yeah, I had a question. So when you were discussing the soft graviton and soft photon theorem, so the graviton theorem involves both angle and square bracket, right? So do we scale both the angle and the square brackets here to get this?
So the rule will be that whenever I take a positive helicity particle soft, and that's what I'll do in this entire lecture, I will scale it, oopsies. I will scale it in this particular way here, that I only scale the angles. If I were to take a negative, I'm only doing one soft limit at a time. So if I were to do it for a negative velocity particles, everything I say today will be the same, except you interchange angles and squares. And in particular there, I would take the square brackets soft instead of the angles. But yes, the amplitudes with gravitons and amplitudes that are not in the MHV sector will depend both on angles and squares in general. But I still only take the angle soft when I have a positive velocity photon or graviton.
A related question to that. So I guess when Weinberg derived the soft graviton theorem, he didn't think of it in terms of spinor helicity, right?
That's right.
Yeah. So is it, do we do it afterwards to match with the soft graviton theorem that he derived?
Oh, excellent. So when I wrote this soft factor here for the graviton in spinor helicity, that was literally taking the expression from Weinberg's paper and plugging in polarizations and momenta in spinor helicity formalism, and then you can rewrite it into this form.
And yeah, and then we take the soft limit in a way so that it reproduces the Weinberg's formula. In other words, we take the soft limit.
It turns out I don't have a choice. When I take the soft limit, it turns out I must get this leading soft theorem. There's no other choice.
It doesn't depend on whether we take the limit on angle bracket or square bracket.
No, it doesn't. Those are really equivalent up to little group scaling, but I'm doing the thing that is most convenient for the easiest derivation, basically. And if you did something else, the powers of epsilon that you would have would change. But in this way of doing it, I'm sort of maximizing the divergences, which means that I can get all these subleading soft theorems as divergent pieces, not as order 1 pieces, which turn out to be more difficult. The idea is that having poles in epsilon is going to be the convenient thing that allows me to use complex analysis to extract these results, as you'll see. Cool. All right, so let's go and try to derive that master formula. So it's a little bit of a long derivation, but I'm going to break it into steps so that at each step you can sort of see the key part. And so the first step, so what I mean here is now let's go and derive the master formula. So step 1 is our intuition. Our intuition is that the divergences come when I take a particle soft and some propagator inside a diagram will go on shell. And that exactly happens whenever I have a cubic interaction. So the intuition is that divergent terms arise from cubic interactions. And they only arrive from cubic interactions. If I had some 4-particle interaction like this, and I take one line soft, the internal line doesn't go on shell when my other momenta are generic, as I will assume that they are. So this diagram here would be order epsilon to the 0. It couldn't possibly a divergent piece arising from it. So again, the soft part comes from basically this type of term here. Okay, now this is very nice because we know a lot about cubic interactions because we know they're on-shell matrix elements. And so in particular, when I take a soft limit, basically I would get something that looks like a 3-particle amplitude if I can take the limit in a smart way that doesn't take the momentum all soft, but if I can sort of go into the complex plane a little bit and put the internal line here on shell, then I can get an expression where these type of diagrams dominate. Let me, this is a little abstract, but I'll explain that in detail. So we know the 3-particle amplitudes very well because we know for massless particles, they're uniquely determined in spin helicity formalism. And that was one of the things we saw last time. So they're uniquely determined in the spin helicity formalism. And this indeed will come in and we'll use it. But then we have to figure out how to take the soft limit. So basically what I want to try to do is figure out a way of taking the internal line here on shell while not having my photon completely soft, so epsilon still a little bit away from 0, such that I can use my factorization on the pole and then take the soft limit and extract information. This allows me to utilize the fact that we know the 3-particle amplitudes very well. Okay, so I imagine I want to take my soft momentum to 0, right? So I want to take this soft, but I want on every step along the way to keep my on-shell properties. So I want to keep all the particles on shell. And preserve momentum conservation. But this is of course tricky because in the limit where epsilon is 0, I must have that the sum of all the other momenta of the n other particles is 0. In other words, I need to have that this property here holds. This must be 0. So how can I, for epsilon not quite 0, keep momentum conservation? And the answer is that we deform the momenta by taking new momenta that we will call PS hat and K hat. And these will be on shell, so I can write them in terms of spinor helicity variables. Like that. And then the question is, how do I do this? So I want this to be such that the sum of all the PK hats to n plus PS hat is equal to 0. That's how, for any epsilon even greater than or bigger to 0, I can get 0. So I know already how I want to deform my momentum S. I want S hat to be epsilon S, because I'm assuming that my soft particle is positive helicity. And I want S square to just be unchanged. But then how can I keep the other particles on shell? What I do is that I choose two particular lines, I and J, in the set from 1 to n, and I'll deform those two lines too. And the answer won't depend physically on which ones I choose. I'll just choose two. And then I set the angle brackets of those to be unchanged, but I'll deform the square brackets in a way such that momentum conservation is preserved for all epsilon. How do I do it? Well, let me show you. I pick.
Can you explain? I'm a bit confused. Like,
Yes.
why can't? Sorry. What is the problem? Like when you write down these momenta in this spinor helicity form, they're already on shell, right? So
They're
the
already on shell, but they don't necessarily satisfy momentum conservation.
Why?
So the point is that at epsilon equal to 0, the n particles by themselves must satisfy momentum conservation. So as soon as I take epsilon a little bit away from 0, I also have my PS, and that will not satisfy momentum conservation along with the other ones. So therefore I deform them a little bit in order to achieve that.
They will depend on epsilon now. Like PK
Exactly.
will also depend
They
on
will
epsilon.
now depend a little bit on epsilon through the following way of writing them.
I see. Okay. Thanks.
So I will, good, very good. So yes, you'll see exactly how this works. I'll deform the square bracket a little bit by a square bracket S times a certain factor. And I'll explain why that factor is what it is. So this is an S. Okay, so this is how I deform the particles. And then what I wanted was, I wanted that the sum over all k equals 1 through n of these shifted momenta plus that of the S. Now I want this to be 0 for all epsilon. And that's what I can achieve by having deformed the I's and the J's. So from these first parts here, these being unshifted, I will get that all the K's then remain on, sorry, here. There's the unshifted part that is just 0. And then there's a part that depends on epsilon. And what is that part? It's epsilon times, and let's start with the thing that came from S. So S angle S square, that's PS, minus then this part that comes from the angled deformed. So the square deformed. So that gives me JS angle divided by JI times S square minus J times IS, and this is from this part here, over angle IJ times square S, and that's the whole thing. Okay, this has a common square bracket S in it. So if I look at everything that is in here, this becomes a square S, I can take that outside, divided by, let's pull out an angle IJ. Then I get S times angle IJ minus, well, I actually get plus because I have to reverse the order here. So I get plus angle I times JS. And then from the last term, I will also reverse these two lines. so that I get plus J times angle SI. And now you see, if you read through each term cyclically, I have Sij, Sij, Sij. This is exactly the Schouten identity. So this whole thing is 0. By the Schouten identity I showed you yesterday, the statement that 3 two-component vectors must be linearly dependent. Okay, so this whole epsilon dependence was 0, and I actually achieved what I wanted by this shift, that I have my momentum conservation preserved.
Question. Is there any sum over I or J in this?
There's not a sum over I and J. I and J was a choice I made of 2 lines that I'm treating differently from the other ones. And I can make any choice between the 1 through n lines. It's just a trick to keep everything on shell, but it's a very useful trick. So now if I compute my p hat ks, this is the momentum that runs in my diagram with my soft line attached to any kind of k line. This has momentum pks. And now we shifted everybody, so this has a hat. So I want to figure out when this thing has poles. And I can plug in, and no matter which of the k's I use, I will find that this, well, it's ks, let me write it out first, k hat, s hat. And because the change in I and j were proportional to s, then when I dot it in with s, nothing happens, because a square bracket s with itself vanishes. So this simply becomes an overall epsilon that came from here times ks, ks. But here's a little thing that is tricky. What I wanted was a way for each k of putting the internal line on shell. And you see that the way I can do this is that the only way this can be on shell, this is only 0 when epsilon goes to 0. That means that the poles for all the different diagrams that factorize in this cubic way, all these different diagrams, will have the poles located in the same place. And that's kind of unfortunate, because then I can't use them as simple poles where I can easily extract the residues. So I want to move each pks equal 0 on shell condition a bit away from epsilon equals 0. So in order to do this, I'm going to use another trick, which is I'm going to do one further deformation of the particles. So here is what we'll do. We'll introduce a new complex parameter z, that's some complex number. And then I'm going to write s hat, not just as epsilon s, but I'm going to shift it a little bit, because that way I'm going to shift the poles that I'm going to show you. But now that I've shifted s by some amount that depends on z, I also have to compensate for that to get momentum conservation. And so then momentum conservation requires that I similarly shift 2 other lines, and I can do it with the same I and j. So let me go up here and steal my expressions. And I'll do it in a way that is very parallel to what we had before. I'll do the same thing, but now I'm adding an additional part that depends on C, an additional shift in variables that is very parallel to what we did before, except with X replacing S. And now momentum conservation for the shifted momentum variables will hold. And it will hold by exactly the same argument I just showed you, because everything I did was the same with X and S interchanged and epsilon going to minus C. Okay, so this here is going to be my kinematics. This will define my kinematics. And what is the use of this? Well, now, when I look at the internal momentum P hat Ks squared, I have Ks hat and hat. and k hat s. Now I can remove the hat from the s square and from the angle k, because there will never be one. And what you end up with is then epsilon times ks, just as before. But now there's the term that depends on z that comes from the shift in s hat, and that will now have k times x, and this multiply ks, because I can also remove the hat there, because it's dotted into s. And now I can write this as epsilon minus epsilon k times pks unshifted squared, where epsilon k is z times kx divided by ks. So what's the point? Let me try to draw a picture of what we have now. So here is my complex epsilon plane. And before I had all my poles located at epsilon equal to 0, but now I've moved them away. By having a non-zero z, I'm shifting them off that I have epsilon 1 there, maybe epsilon 2 there, epsilon 3 here at some other point, and epsilon n, etc. up there. And we'll be working in a regime where my z is less than epsilon, which is much less than 1. So we're looking at small epsilon and even smaller z, in such a way that what I'm interested in to extract the divergent part of the amplitudes, the epsilon divergent part, is a small region around the origin here. So I'm looking at a small region here. In that small region, I know exactly how to compute the residues on each one of these poles, because I know that on each one of the poles, they correspond to an internal propagator going on shell into a cubic amplitude and an n particle amplitude. And then I can extract a lot of information from that. So on each pole, so on each of these poles, I have factorization. And the key point is that I can factorize on each of these poles a little bit away from 0. And once I know an expression there, I know those are the only pieces in the amplitude that can possibly give me an epsilon divergence. So then I can take epsilon to 0 while pushing t to 0, and I can extract the divergences that way. And they have factorization into A3 times AEN. So this gives me step number 3 in the process.
Can I ask you a question?
Yes, of course.
I think I didn't really understand why it is important to move away the poles from the origin. Can you repeat that, please?
Yes. So going back to the diagram that we know gives the UV divergences, I know that if I take the internal line here on shell, that means PSK. If I take it on shell, this will factorize into a free particle amplitude that I have control over because I know what all of them are, times some leftover n particle amplitude. And that is very much in the spirit of what the soft theorems look like. They look like some factor times an n particle amplitude. But the problem is when all these poles get stacked up on top of each other, I can't figure out which part belongs to k and which one k equals 1 and which part belongs to k equals 2, which part belongs to k equals 3. But when I separate off the poles, I can calculate the residues on each of these poles, which correspond exactly to such a diagram here. Does that answer your question?
Yes, thank you.
Great. So basically now we look at a given pole, and or we can say near the pole, near each pole. So I look at one particular pole, K, and I look in a small neighborhood, and you can think about doing a Cauchy type of theorem in that neighborhood. Or I can simply express my n+1 particle amplitude as something that contains a part that will be shifted because it depends on S and on epsilon, and so this depends on Z and epsilon. So it depends on a shifted amplitude. This picks up exactly the part with S and K, and then the endpoint stuff. So it has the free particle amplitude with S and K and the internal momentum. times some n particle amplitude with line k being special. And this must be then divided by pk s squared. And here in the numerator, up here, in order to write this, I must have taken pk on shell. So in this expression, pk s squared is taken to be on shell, which is equivalent to saying that epsilon is epsilon k. So I basically pick up the one contribution to the amplitude that has this vector adjacent channel, and I pick it up uniquely. And the power of this is that there are no other diagrams that can contribute to the amplitude. So an plus 1 will be a sum over these poles, epsilon k, with k equals 1 through n, of this type of expression. Let me steal it from up here. Like that. Plus, the only other thing that can be here is order epsilon to the 0. This is the only thing that can give me a UV, that can give me an infrared divergence, because everything else would be order epsilon. And that's really all I care about. So in other words, what I benefited from here is that if I think of the small region around the origin that surrounds all the poles, then I can pick up the residues at all of these poles and add them up. And I know that in the limit where epsilon goes to 0, these are the only places that can give me divergences in epsilon. And therefore, I can determine the entire divergent part of the amplitude as epsilon goes to 0 from this. Okay, so that's the first step of doing the factorization. But then I need to worry about what each of these pieces are. So from what we had before, I know that this propagator part is something I can write as epsilon times 1 minus z over epsilon. I'm just factorizing out epsilon, kx over ks. And you might be worried that I'm writing things with 1 over epsilons here, and I want to take epsilon to 0, but this turns out to be a very nice way of writing it. And this is just the same as epsilon minus epsilon k times pks squared. And here I still need my pks squared also. The only other part I really need to worry about is what sits inside the free particle amplitude. And free particle amplitudes, as we know, is something that we have very good control over. So what can this part possibly be? So A hat free has free momenta S and K, and the momentum PKS. It's going to be some coupling, which can be different for different Ks. So I'll give it a subscript K. Then times S square bracket with K to some power x1, K P. I'll drop the subscripts on P just to keep it simple. And then P hat S to some power x3. And we know from last time from our little group scaling that the x's depend solely on the helicities of the free particles involved. Just the way a free particle and a free point correlator is determined in CFTs. And we know also from last time that the mass dimension of the coupling is 1 minus the sum of the helicities. Now, in order to evaluate what each of these brackets are, I will need to know what P hat is. And I'm happy to show you the calculation if there are questions about it afterwards, but for now, let me simply give you the answer. So one can show, and you can feel free to ask if you'd like to see the details, that P hat KS square bracket is equal to K minus Z times XS divided by KS times S square bracket. Okay, one step at a time, we're almost there. So using that, we then have that sk hat is simply sk because the shift by an s square bracket just gives nothing when you dot in another s square bracket. Then p hat with s will likewise give ks because you only pick up from the first piece. But in k with p hat, I eliminate the first piece, that one, and pick up minus z times xs divided by ks, multiplied by square bracket ks that comes from this part here. So why did I compute these three square brackets? Well, because those are exactly the one that sit up here in our free particle amplitude. So now we can rewrite it. When I put all these pieces together, I know what my three particle amplitude is. I plug it in back up here, and I use what my denominator is. I will have derived, and I'll leave the algebra to you. I'll have derived the master formula. So let me write down what the result is once all things settle. It is the following, namely that the n+1 particle amplitude deformed in z and epsilon is going to be equal to the sum from k equals 1 to n of gk times sk square bracket to the 2hs minus a number that I'll call a, and this a that sits here will be equal to the mass dimension of the coupling plus 2 times the helicity of the soft particle, whatever that might be. Then there's an angle bracket xs to the 1 minus a. Then there's my shifted z-dependent n particle amplitude that just came along to the right. There's a factor 1 over epsilon, a factor c to the a minus 1, an angle sk to the 2 minus a, and then 1 minus z over epsilon, and I'm going to need a little more space to write the last bit here, times xk divided by sk. All right, and that's the whole thing, plus, of course, order epsilon 0. And that is then our master formula. Maybe it doesn't look very much like master, but now we can start having some fun with it. Okay, the first thing that you see in this formula is something that is a little curious. Namely, and actually maybe I should just pause for a second to see if anybody has questions.
I have a question.
Yes, Stefano.
That z parameter that we introduced seems to not be a physical parameter, right?
Exactly.
So how come that it enters master formula? I guess when you actually compute some amplitude, you have to take the limit z to 0 and then see the behavior of the amplitude when epsilon goes to 0. So you need limit for z to 0 first.
Precisely. So we were working in a regime where z was less than epsilon, much less than 1. And now to get things like soft theorems, I want to take epsilon to 0. But in order to do this, of course, I also need to take z to 0 in order to preserve this. And now we see something very awkward, namely that whenever a is greater than 1, we're going to have poles in z, poles at z equals 0. And as you said, z was just an auxiliary variable. And we know that our amplitudes are only allowed to have poles where physical particles can be exchanged. In particular, it is certainly not allowed to have any kind of poles in some random variable c. So particles, physical particles can be exchanged. So they're in particular not allowed to have poles in any kind of value of C, in particular not at C equal to 0. So this
Can I ask another question?
Yes.
In the derivation of the master formula, where did you have to use that Z is less than epsilon?
So the way we used it was that I'm interested in an epsilon going to 0 limit. So I want to move these poles just a little bit away from 0. But in the limit where I take epsilon to 0, I need them to all go back to 0, basically.
Okay.
That makes sense?
So, but in the derivation of the factorization, Z and epsilon are actually
They're completely arbitrary from
That's
that
my
point of
question.
view. It's only at the poles they have a relationship. Very good. Okay, so I'm not allowed to have any poles, but in this formula, I have some sum over things that whenever A is positive, or sorry, is greater than 1, I obviously will have poles. So the only way to resolve this is that somehow they're actually not poles, that when I do the sum over all K, the residues of these 1 over C or 1 over C to some power poles must cancel. So it must be, the resolution is that the Z equal to 0 poles must have vanishing residues.
They can also be branch cuts, right?
The what, sorry?
They can also be branch cuts, right? Because
There can't be any branch cuts because I'm just a tree level.
no, but well, GK is always an integer, or
GK is just this is just a coupling.
so well, then A can be fractional, right? So A minus 1 could be, there's Z to the A minus 1 in the denominator.
No, it actually doesn't turn out to be fractional because the mass dimension of the coupling has to be an integer.
Oh, sorry. Yeah, okay.
And then even if I have
it.
half integer spin, I have 2 times the spin of S. So I will take fermions to 0 in these soft limits also, but there's a factor of 2. So A is actually, this is an integer.
Okay, thanks. Yeah.
Excellent, good. Okay, so let's try to see what we get out of this. And these statements, these fancy foundational statements I made in the beginning, that gravity equivalence principle, so and those actually exactly will come out of the requirements that these residues at C equals to 0 vanish. So it gives a very fundamental result. Okay, so let's now apply the story. Okay, we'll start with soft photons. And very good. We'll start with soft photons. Photons couple canonically to things like electrons and other things. We're looking at canonical couplings. So I want to look at cases where my coupling has no mass dimension, so that is dimensionless. If I do a dimensionless thing here and my soft photons, I take the positive helicity one, that's what I was focusing on all along, then my A parameter is going to be 0 plus 2 times the helicity. So A is 2. And precisely now we're in the situation where my AN plus 1 hat has a 1 over C pole. Because A was 2, and I go back to my formula, and here I see I get C to the first in the denominator. So let's grab our formula here. Actually, I will grab it so I can use it multiple times later. Here we go, and see what it gives us. So here's our master formula. Okay, what do I get? So I have A equals 2, and I have HS equals 1, and I plug into here, and I see that the vanishing of the 1 over C divergence, that residue, says that the sum of K equals 1 through N must be equal to whatever the coupling is of particle S, the soft photon, to particle K, times, well, 2 times hs minus a, that's 2 minus 2, that gives me 0. So there's no square bracket, sk goes to the 0 power. I have an xs angle bracket to the minus first, but that's independent of k, so that will go outside. I have this guy here evaluated at 0 because I'm taking the residue at c equal to 0. And the epsilon, I'm just going to factor out. That doesn't matter. Well, I can write it. And then I have sk angle to the 0 power. And I'm looking at the residue at c equals 0, so I get times 1. Okay, all in all, what this implies is that what must vanish is that the sum from 1 to n of gk must be 0. That seems like a very innocent constraint, but what does it mean physically? It means that charge must be conserved. So this is exactly the statement of charge conservation. It says that whenever I have photons that couple minimally in the sense of zero coupling dimension to any kind of particles, whether they're electrons or muons or whatever they are, the charge associated with that coupling must be such that in a non-vanishing amplitude, they add up to 0. So that is exactly what the standard charge conservation of electric charge says. So last time, in the first lecture, we talked about symmetries, and I said, oh, if your Lagrangian has a global U1, then you get ward identities for the amplitudes that satisfy, for charge conservation of that U1 charge. Here we're doing something different. We have no Lagrangians to refer to. We just use statements of locality and factorization, and we automatically get the statement that whenever you have photons, you have charge conservation. And that's pretty cool. So you kind of get it out of
one question.
Yes.
How did you get rid of the a hat k? It depends on k, right?
Well, it depends on k, but it depends on k in a very innocent way. So you're asking about this part here, that when I set c to 0, there can't be anything in this case in that remainder of the amplitude that depends on k. It's basically just the same amplitude that we'll get when I take the amplitude and I remove my photon, it's whatever is left. So as long as this part is non-zero, it will be the same for all k and factor out of the sum. But that's a good question if there can be loopholes there, but in this case, there cannot. Okay, so now we have charge conservation. We got that for free. That's kind of nice. Of course, we knew that should happen, but it's nice to see it from this context. Then, well, what happens is that the order c to the 0 terms, those are the ones that will give the soft theorems. And so let me show you how that works for the photons. So now I look at terms in this expression that are the order z to the 0 type terms. And I see that in order to get those, I have to take this denominator factor, and I'm going to expand it in small z. So what will happen then is that the z that comes from here cancels the z that came from there, and I'm left with a 1 over epsilon squared term. So I get something, let's write it as an arrow, that depends on 1 over epsilon squared. And then I have to see what else I get. I basically have all the same factors as before, but now they get multiplied by something else, namely the factors that came from this expansion here. So I have my 1 over xs that came from this piece here to the -1. And then I have the two factors from here, so they give an xk divided by an sk. And that multiplies an evaluated at c equals 0, so it's no longer shifted. So that means that it's just an. And again, in this case, just as before, there's actually no k dependence. And what this is, oh, and I forgot my gk and then my sum. Let me get those in. So I have my sum over k, 1 through n, and gk. And this is exactly the thing that I called the soft factor from before. So this derives for us the leading soft theorem. And then you can get the subleading soft theorem with S1 by taking another way you can get an order C to the 0 term is to expand the amplitude here. So you can get C times dC of AZ hat evaluated at C equal to 0. And that will give you the soft theorem. So this comes with some factor that depends on this, and that is related to the fact that there's actually a derivative operator that corresponds to the angular momentum operator that sits in those subleading soft factors.
Can I ask a question?
Yes.
So maybe this is just a coincidence, but that's why I'm wondering. So is it always the case that, or that when you look at the residue for Z, that you end up with some kind of symmetry statement?
In a sense, you will see another statement that you'll get soon, but it actually is the case that you end up with something that is an amplitude consequence of a symmetry.
Okay. Okay. Thank you.
Cool. All right.
Can you
Yes.
remind what is X?
X was what actually came from the polarization vectors that gauge freedom in the polarization vectors.
So X is basically epsilon.
So in the traditional way, no, X is not, well, no. Okay, so in this derivation, the X came in through this arbitrary shift I did of the momentum variables.
Okay, fine, good.
So I just looked at like a totally arbitrary thing that I put in.
Mhm.
But when I told you in the beginning what the soft factors were in spinor helicity, let me find it right here. Then X came in as the arbitrary gauge, the gauge freedom in the polarization vectors. That was this X. It turns out to be
Oh, that's
exactly.
right. I remember now. Thank you.
So it's kind of cool that in this arbitrary shift way, I just introduced it as a convenient way of moving the poles off from epsilon equal to 0. I had some arbitrary parameter that actually gets connected to the arbitrary choice of the arbitrariness and the choice you have of polarization vectors. There's a very nice connection there.
Cool.
Okay, soft gravitons. So here, a positive velocity graviton has H plus 2. And what is the coupling dimension I should have for gravity? We saw that last time when we calculated the free particle graviton amplitudes. That's the dimension of kappa. So this should be -1. And so when I do this, I find that my A is minus the coupling dimension plus 2 times the helicity, and that is then 3. Okay, so yes.
Can I ask a follow-up question about the previous one? Sorry, I had some problems with the mic. I wanted to know, but it seems like your result depends on X, but X is an arbitrary choice. So why is that the case?
So in my polarization vectors for photons, I had something that looked like X sigma bar P for the photon, which is in this case XS. And it looks like that. So there was some expression that looks like this. And what that was equivalent to is changing X corresponds to shifting the polarization by something proportional to P. So that is that kind of gauge freedom that you have in your choice of polarizations. In other words, your polarizations have to have some normalization condition, and they have to be transverse to the P's. But other than that, you have a freedom in choosing them. And that's a gauge freedom that sits there.
Yeah, my question was just that pole that you found that with the soft theorem, that 1 over epsilon squared term, isn't that a physical quantity that shouldn't depend on X, on the choice of X?
Well, yes and no, but it depends on the polarization vectors. But it's a universal factor, and you can write it in the sort of non-spinor helicity form, but has a dependence on the polarization vector. And I'm free to choose that polarization vector. I can shift it around. I can do different things with it, and that's basically what X encodes there. Okay, so gravity. Now let's get our master formula back into the game again. We'll squeeze it down a little bit in size. And now we have A equals to 3. So we're even in worse shape. Now we have a 1 over c squared. And we have to calculate its residue. And so what is it? We want the residue to be 0. So we take our sum over k equals 1 through n, and now we have a equals 3 and hs equals 2. So what do we get? We get whatever the coupling is times sk now, and this will be to the first power, because it's 4 minus 3 that sits up here in this part. We get a factor, which is xs to the minus 2. That doesn't matter, that goes outside the sum. We get our amplitude an evaluated at 0. And then we have epsilon, we have c squared. Well, it's the residue I'm computing, so there's no z. And then I have sk here to the minus first. And this part here doesn't contribute anything at the leading z pole. Okay, so what this means is that the condition for getting a 0 residue is that the sum k equals 1 through n of gk becomes sk times ks. That has to be 0. The other factors don't depend on k, and I can get rid of them. But this is momentum conservation. This is basically pk, dotted in with some s's. So if it happened to be so this has to hold for generic momentum. And so this can only hold, and it will hold by momentum conservation, provided that all the couplings are exactly the same and they're present and non-zero for every k. So in order for this to hold, so this will hold by momentum conservation if and only if all the gk are the same, and we know what that same is, it's kappa. So the physical statement here is that the graviton must couple with the same coupling k to all other particles, in particular here, all other massless particles. And that is the amplitudes version of saying the equivalence principle, that no matter what an object is made of, it will drop the same in a gravitational field. So that is the equivalence principle that comes up. You could have imagined perhaps that a graviton coupled in a different ways to a fermion or something like that, but this shows you that that's simply not allowed, and that's the equivalence principle. Then you can go ahead and you can look at the order C to this. Oh, actually, I should make one more step, which is looking at the 1 over C term. Once you have the equivalence principles, there's no further constraints, and I'll leave it as an exercise to see that. And then from order C to the 0, you get this graviton soft factors. And again, that is a nice little exercise to see how that works. Questions?
You have about 6 minutes left.
Got it. Okay.
Sorry.
Yes.
Can you, from this master formula, also derive the J tildes and the S tildes, or are those more complicated?
Exactly. Yes, you can. So the S tilde 1 for the photon soft theorem and the S curly S tilde 2 for the graviton theorem, they come from higher derivative operators. So that means instead of having the massless coupling for photons or the dimension -1 coupling for the graviton, you look at higher derivative contributions, and they are the ones that contribute to those. So these comes from higher derivative terms.
Can I ask something?
Yes.
So you're working exclusively with massless particles here. So does this equivalence principle only hold for coupling of gravity to massless particles?
No, you know that gravity also couples the same to massive particles. It's a statement that basically says that gravity couples with energy, as you can tell from this part here. This part here is really pks squared, which is the center of mass energy. for S and K together. So you can see that it holds in that sense. And for massive particles, you just also have the mass that it couples to, not just its kinetic energy. But the equivalence holds too, but I can't access massive stuff when I'm just inputting.
Right, so it doesn't, I mean, this does not cover that.
It just does not cover that case. Okay, so the last thing I wanted to show you in the remaining 4 minutes is the statement I made in the beginning about what about higher spin. So I'll just do an example. So the example goes like this. Suppose that I have some spin-free particle. The equivalence principle would tell you that it must couple to spin 2 in some way. So say that I have some spin-3 particle and it couples to my graviton. And let's suppose we can think it couples to some other particle X, but let's just say that it couples to a negative velocity spin 3. Let's suppose you have such an interaction. Doesn't seem to be much wrong with that. I know what the mass dimension of such a coupling would be, because that's given by the free particle spinor helicity, bootstrap of the amplitudes at 3 point. And it's 1 minus the sum of the helicity. So 1 minus 3 plus 3 minus 2, that gives me minus 1. And spin H, if I want to consider the spin 3 particle soft, it has 3. So my A is now going to be minus 1 plus 2 times spin 3, and that gives me 5. It turns out that you can consistently prove that A cannot be 4 or greater. That doesn't exist. But that's a more general argument. Let me just present it for this case why this is ruled out. Looking at our master formula, we have z to the a minus 1. That gives us 1 over z to the 4 pole.
Sorry, I have a question.
Yes.
You said a cannot be greater than 4?
Right.
Or less than?
It cannot be greater than 4.
Okay.
So if I knew that already, if I had proven that to you, then I can already rule out this case, but I'm just going to show how this case is ruled out.
Okay, I see. Thank you.
Okay. So if I go ahead and I use the formalism from our master formula, let me just tell you what the condition from Renison residue is. And that is that 0 would have to be the sum over k equals 1 through n of gk sk xs to the minus 4. We don't really care about that part, divided by sk to the minus 3. That's what you would directly get times an at c equal to 0. And generically, there's nothing that is like momentum conservation. There's nothing that helps me in any way here, because the powers of the angle sk and the square sk don't match up. So generically, there's no way I can make this 0. So there's just no way I can tune the couplings, which is all I have to play with as numbers, or do anything else that can make this 0. So this is generically always non-zero. And therefore, I can conclude that spin 3, massless spin 3, cannot couple to spin 2 via an interaction of this form here. And so, of course, you could say that's not so powerful. You just showed me one particular coupling, but you can do this much more systematically and prove that higher spin can't be there. This was just one example of it. And it really relies on the fact that you can never get rid of the residues of the z's. And so the last thing you could do is to consider spin 3 halves. And it turns out that from that, you will necessarily conclude that these particles these gravitinos must couple to gravity in the supersymmetric way. So you get another symmetry out of the vanishing z residues, which is the SUSY ward identities, supersymmetric ward identities. So if anybody's interested, I'm happy to share some notes on that. But for now, I think I'll stop and see if there are questions from today's lecture.
Thanks, Henriette.
I have a question, and this may be naive, but I'm just confused about something. So in gauge theory, the gluon couples with the same coupling to every particle. We don't call that equivalence, right? I mean, because it's not a statement about inertia.
Does it couple?
It's just
to
a statement of
the-
gauge. It's just a statement of gauge
That's
symmetry.
a statement of gauge symmetry
Right.
in a sense. But I yes. So wouldn't I technically have some freedom in how I set up? So of course the gluons will have to couple to themselves in a way that's dictated by gauge invariance.
So say in 40 n equals 4, there's a whole bunch of particles, but just a single coupling.
That's right.
And there's no principle of
But
equivalence over there.
if I give up on the supersymmetry part, am I not allowed to have different quarks couple in different ways to gluons?
There's Yukawa couplings that are different, but the gauge coupling is one.
That's right. The gauge coupling, yeah, you're right. I mean, the gauge coupling is one. I mean, it's sort of captured by the fact that I have FABCs all over the place. I think that's right. Yeah. So yes, we don't call that the equivalence principle, but you also have an important fact in QCD or in Yang-Mills theory, which is that the gluon doesn't have to couple to everything. And that's the difference, right? So what the statement here was that I could only get the pole to vanish when this entire sum was here, because I needed that every term here to use momentum conservation. So graviton must couple to every possible particle in the spectrum. But for the gluon, I can certainly have Yang-Mills theory, and I can have some electrons in it that are not charged under the non-abelian symmetries, that are just singlets, and the gluons don't touch them, they don't couple to them. So it is different from gravity in that respect.
I see.
I had a question.
Mhm.
Yeah. So when you were discussing the master formula for soft photon, can we use that to also describe soft gluon theorem?
Yes, you can.
And we don't have to worry about any color ordering or anything.
So when you do the soft gluon theorem, and that comes back to the exercise that we did before, if I'm looking at a gluon amplitude with some particular color ordering, then because of the color ordering, the sum over k gets reduced to a sum of who the soft particle is adjacent to. So in that case, if I just wanted to extract the soft particles, I would only need to worry about S next to 1, and then the rest of that, plus S next to N, and the contribution to that. Because of the color ordering, that's the only thing it's adjacent to and can attach to in this manner. With color ordering, I'm not allowed to cross lines or interchange the labels. So from this point of view, it just reduces the sum. It's some basically means the same master formula, but some GK is automatically 0. And this is the sum of these two contributions is what you need to do the first exercise I mentioned earlier on the lecture. Connect these type of diagrams of polarizations to what you get from the soft limit of Park-Taylor. So there's a paper on the subleading, so the gluon subleading soft theorem that was done shortly after the paper by Cachaso and Strominger for Gravitons by Eduardo Casali. So that's a paper where you can look that up. It's a very short paper. You can see the details.
Another question I had. So I have seen that, I mean, you discussed the soft theorem and the subleading soft theorem, but I have also seen people discussing subleading soft theorem.
Yes.
So is there a limit to that? How far we can go from the amplitude perspective?
Yes. So let me go back to where I wrote these general formulas in the beginning. Right here. So for the graviton, there's the leading soft theorem, the subleading, and then the sub-leading soft theorem. And you can see from the master formula that that's all you can have in terms of divergent limits in epsilon. The things that are order epsilon don't necessarily have any kind of universal form. And that's the key difference. So one of the reasons we studied this in the first place in 2016 was the question of whether higher derivative operators could possibly change these soft factors. which came from the question of whether these soft limits would also be universal, these subleading and subleading soft theorems would also be universal in loop amplitudes, because these were tree-level results. And I mentioned all this before, but a subtlety at loop level is the IR divergences that arise in the loop calculations. But you could restrict yourself to a simpler context, which is the case where you get loop correction from massive particles. Those loops from massive particles, I could integrate out the massive particles by taking the very massive and ask what kind of effect that leaves in terms of effective operators. And so that's actually why we sat down and studied in generic effective field theory, do these soft theorems change at all? And somehow nobody had ever asked those questions before. And it turns out that for photons, it can change the subleading soft theorem. And in graviton, it's only at subleading order. And this was quite important because in these celestial amplitudes and asymptotic symmetry approaches, the subleading soft theorem played a very important role for connecting things to the BMS algebra. And it would seem that the universality and the ideas that there could be some kind of flat space 2D holography at null infinity, that would rely on these theorems at subleading order not to be corrected. And so it was actually quite important to be able to prove that at subleading order in the soft graviton theorems, there can't be any corrections from loops of massive particles at least. But there can be at subleading order where it plays less of a role. There are papers by Ian Stewart at MIT and collaborators that look at massless loops. But again, you have the issue there of IR divergences built into the story. So you have to figure out what object you're actually going to look at. What is the physical object that you're studying?
Sorry. And if we want to go even higher up in the order, then we would have to analyze higher powers of, or higher poles of Z, right?
Yes. Oh, so good. Yes, sorry, what did you ask?
So I was just asking, if we want to go even higher up in the order of these corrections, then we would have to look at higher order poles of Z?
Yes,
I
but
think
that's not so much the stumbling block. The stumbling block is that when I look at the master formula, I had control over all the epsilon poles because they came from this picture of moving all those poles that contribute away from the origin. But it leaves all the order epsilon to the zero term that I generically don't have any control over. So you could try for specific amplitudes to write down answers for specific couplings, but it's not clear that there's a universality in the same way that there is for the divergent terms.
Okay, so that would depend on the specific way this A and amplitude look, and we have to go case by case for that.
Right. So by the way, there's also in the chat a nice comment on the question about this equivalence principle in QCD's question. So Ethan Neal commented that quarks could be charged under different representation of the gauge group, of course. And Thomas said the effective couplings could be different and so on. So anyway, so the gluons are not at the same level as the gravitons in terms of equivalence principle, as we can conclude.
Right, yeah, I get that now.
So, so the last lecture tomorrow will be about the double copy. So we'll use what we know about poles and factorization again, and try to figure out how double copy and such a thing can even possibly work. And that will be the subject for tomorrow.
Okay, great. Sounds good. Let's thank Henriette again. And maybe if people want to ask questions, you can hang out here or go together.